pick up where we left off last time. Suppose that in a vector field F is a conservative vector field. So F is a gradient of little f for some function little f. So this is what we're going to focus on more today. For instance, if you have a vector field that is conservative, how do you actually find little f? We're going to learn how to do that today. So what we covered at the end of last time was this, that the line integral of such a vector field over a curve C is, so C is parameterized by this given function, r of t, where t goes from a to b. So we have, write everything in terms of t, but that is the gradient of f dotted with r prime, which by the chain rule is a derivative of a composition f composed with r. So then we just have the derivative and the integral canceling each other out, and we get f of r of b minus f of r of a. So evaluate your function f at the, you plug in the endpoints, the initial terminal points of a curve, and that's the integral. So this is the fundamental theorem of, oops, a little too much space in there. The fundamental theorem of line integrals, which you can recognize as being much like the fundamental theorem of calculus. In fact, if f, either f, big F or little f, is a function of just one variable, then this is essentially the fundamental theorem of calculus.
On the top part where you have the information,
Yes.
second R.
Oh, that should be a prime.
Okay.
Yeah. Okay. So, so certainly, if we have a conservative vector field, this is a much easier way of evaluating the line integral than trying to evaluate this directly. Now, so let's take a look at the consequences of f being a conservative vector field when it comes to the case where this curve C is a closed curve. So, and this is the very last thing I mentioned last time. Okay. So basically, this is a curve that begins and ends at the same point. Then, we're evaluating f at the same point, we're just going to get 0. Alright. Now, so now let's do this. Let's take this closed curve C, and I'm going to divide it up into two curves. So we'll have this curve C1 that goes around from here to here. So this is the initial point A. And then we have curve C2 that starts here and completes it. So C1 is the top part, C2 is the bottom part. Well, because the integral over the entire curve is 0, that means that we can just break up this integral to integral over C1, integral over C2. Then let's take C2 and we'll reverse the orientation of it. So I'm going to make this go the other way. So as the parameter increases, now we're going from here to here. So both curves, C1 and minus C2, have the same initial point, same terminal point. So that means I can do this, because once I change the orientation, of this curve, use minus c2 instead, that changes the sign of the integral, so this plus becomes a minus. Okay, so now this is 0. So that means that the integral over c1 is equal to the line integral over minus c2. No, they're not both equal to 0, but they're just equal to each other. So starting from this point, it doesn't matter whether we took this path or this path, we get the same result. In fact, you can show that it doesn't matter what path you take. The value of the integral of your vector field f from this starting point to this ending point, no matter what path you take in between, is going to be the same. So if, this is very important, the whole time we're assuming that f is conservative. And the line integral from this point capital A to this point capital B is path independent. Okay. Now, okay. Now, in fact, if we are careful about our assumptions, the converse statement of this is true. Here we are saying if we start with f being a conservative vector field, the line integral is independent of path, which is very nice because then all you got to do is apply the fundamental theorem of line integrals and evaluate this function little f at the endpoints. So you don't have to care about the path that is taken in between. The only challenge is how to get a hold of little f from big F, and that we will learn how to do a little later. So you don't have to bother with coming up with the right parameterization of a curve and working out this dot product and integrating all this. You don't have to do any of that. Okay. Now, what about the other way? If a line integral is path independent, is it the line integral of a conservative vector field? What?
You always need like stuff.
Business.
Okay. So, suppose you have some vector field F. You don't know if it's conservative or not. Okay.
Now, conservative means when it travels in the circle, the integral is 0.
Well, we haven't really shown that those are completely equivalent.
Okay.
What we have seen is that if it's conservative, then this is true.
All right.
Now we're going the other way. If we start with this, is it conservative?
Okay.
All right. So now this being equal to 0 is the same as saying this is path independent between any 2 points in a simply connected domain. And I'll give you informal definition of that, and then I'll draw a picture. No holes. So if you have a domain like this, say in the two-dimensional case, all right, so this is an example of a simply connected domain, and what that really means is if you have any 2 points in the domain then